Today, we are going to look at estimating area with Riemann sums. I'm going to kind of go, oh, don't write down what I'm doing right now, just watch. Before, if I gave you this, right, you know how to find the area of that. That area is a 1/2 base times height. No problem, it's a geometry figure. But if I were to give you this, right? Now, all of a sudden, you don't have a way to find that area, correct? Now, tell me this. If I were to draw little tiny rectangles inside here, right? Really skinny rectangles. If I were to draw those, could you do the width and the height of these rectangles? You could. And if you found the width and height of every rectangle, if I did them all the way down, could you add those up and get a pretty good idea of the area? You could. And that is what we're doing today. Okay. These are called Riemann sums. And we're going to look at those. If you were given this one, right? Let's look at this. Okay. So from 0 to 2, I'm here. That's that area, right? And then from 2 to 4, I'm here. And then from 4 to 6, I'm right here. Now, if you look at that area as a whole, we don't have a way to find that area. It's a weird shape. But you can break it. I could break 2 trapezoids and a rectangle, and I could add those up, right? I could add green, pink, and blue, and I could have since these are straight lines, I could get the area exactly. What we're going to look at today is doing that with a curve. Okay, so notice we have 4 types of curves. So I want you to really look at this. You're going to need this to answer content style questions when we do our work. So a left sum, a right sum, a midpoint sum, and a trapezoidal sum. It's always weird when that thing talks, right? Okay, so if we use a left sum, right, we're making little rectangles, but when we use a left, we go up to the curve and we use the left dot to make our height. Now compare that to a right sum. If I'm doing a right sum, look at this triangle right here. I'm going to go to the right side and I'm going to go all the way up here and I'm going to have this triangle. Do you see the difference in my pink and green triangles? Y'all see that? Now let's pay attention to some details. These are content questions. This curve is increasing and I'm doing a left sum. So what do you notice about right here? There's area that I'm not actually getting, right? It's not in there. So what I'm doing is I'm getting an underestimate on this side of my curve. Now, if you look at a right Riemann sum, now I'm using the right side. If the graph is increasing, which it is right there, I have more rectangle than I should. So over here, I'm getting an overestimate. Y'all see that? Now, what happens when we turn the tables and now we're decreasing? Now I'm decreasing. My curve is going down. So when I use a left sum, I'm adding more in than I should. So now I'm on this side, I'm overestimating how much is there. And when we look at this one, when I do a right one, that means I'm using this right height and going over. Now, all of a sudden, I'm not getting it all. And what am I getting? An underestimate. So look at that for just a second. This is a think time. And I want you to look that when your curve is increasing, a left is under and a right is over. But where your curve is decreasing, a left is over and a right is under. I mean, that makes sense, right? Because you're drawing rectangles. And we'll do some real ones in a second. We're just kind of doing an overview right now. The other thing I could do, instead of using a left, look here at this. A left would be this dot. And a right would be this dot. I can also use the midpoint instead. And if you look at the midpoint, each box will have a little bit of under and a little bit of over. Do you see what a midpoint is? When we say midpoint, that means we're using in between these, the left and right, we're using that center dot as the height of our rectangle. And then of course a trapezoid, I have the left dot and the right dot, and then I connect those, right? Now just glancing at these 4 pictures, and then we'll actually do a problem with each one. Which one looks the most accurate to you? Yeah, a trapezoid looks the most accurate. Now we're going to actually do the area of the rectangles and see. You know the area of a rectangle's length times height, base times height, whatever you want to call that. What is the area of a trapezoid? We need to recall that. It's 1/2 base 1 times height. Now, I want you to look at where these things are. This is your trapezoid right here. So the height, I'm going to color my height pink. The height is this number here. Base 1 is going to be this. And base 2 is going to be this piece. Do y'all see that? These are your 2 bases, because really the trapezoid, we need a right angle, right? So really the trapezoid is right here. So the height is a right angle. So the height is going to be X, right? So it feels a little backwards. We usually think of height as Y, but this trapezoid is on its side. Does that give you a little overview so you know where we're going? And our goal, our main goal with this, we are finding the area under a curve. Really between the curve and the x-axis right now, okay? We're pretending we don't have calculus, because if this were calculus, we've already looked at these, you would put the integration symbol and you would go from 0 to 5 or wherever, and you would use calculus. Well, if I don't give you an equation and all I give you is a picture, do you have an equation to use? No. So we have to approximate with rectangles, because we don't have the formula to use calculus. We don't know what the equation is. So let's do this. We'll try one of each. They're very easy. We're going to do a left, a right, a midpoint, and a trapezoid. And I want you to notice that I gave you the table of values, okay? Because in reality, this would be data you would collect, and you want to be able to use that data. You don't actually want to have to draw all of these pictures. We're going to do it once with drawing them so that you can take your math and compare it to the table, and you're going to make a connection and say, oh, that's all I have to do. But we need a picture first, okay? So using a left Riemann sum, that means the left side is your height. So let's look at that. This is left. So I'm going to go up, right? And that's my height. I'm going to draw the rest in pencil. So then I go over to the next dot and I come down. Does everyone see where I got that rectangle and why I went up instead of to this dot? Now on this one, where it's a right Riemann sum, okay, I would make my box go up here, right? And then the right side, are y'all looking? This would be my height, so I would go over there. Do you see the different sizes of these boxes? I'm doing my left one in blue, my right one in green. This is the important part right here. for you to see where we got the height. Do y'all all see the difference in those two rectangles? A rectangle has to have a left and right side because those are going up. And for left, we use left. So what's the area of this rectangle right here? What's the width? It goes from 0 to 20, right? So it's 20 wide, right? Width times height, and the height is 120. That's one rectangle. What is this rectangle? I'm gonna write too big, so I'm gonna start down here. Okay, so what is the width of this rectangle? Still 20. And what's the height? It's 100. So everybody see that? Now we're going to have to make more rectangles to get the whole thing. Notice when you switch from left to right, your width is not going to change, only the height. All right, so let's finish this thing. So we're going to go left and down, left and down, left and down. Just looking at this picture, do we have an overestimate or an underestimate? It's going to be an over, isn't it? Because, okay, it's good to notice that. Now let's do the right Riemann sum. That means I'm using, look how I go to my right dot and I connect it over. Now, because this curve is decreasing, is this an overestimate or an underestimate? Let's go ahead and find the area of all these rectangles. What is the width of this rectangle? It's 20 to 50. So that's 30. And how tall is it? 100. Then the next one is also 30 times 80 plus, now 80 to 100 is just 20. And how tall is that? 50. So I'll let you take a second and punch those into your calculator and find us that area. And what did you get for your area? Anybody finish? Punch it in. Did y'all get 8,800? Right, and it's the area, so we could say units squared. Now let's do our right Riemann sum. So this was 20. Notice the x's, whoops, the x's will stay the same, so it's going to be 30. But how tall is this box now? 80. This is still 30 wide, but how tall is it? 50. And this last one is 20, but it's only 20 units high? Yep. So punch that into your calculator and tell me what you get. Y'all got to back me up. Come on. I added it up and got 6,300. Make sure that's correct. So as you predicted, the left one was bigger. This is too big. We know that 8,800 is too big. It's an overestimate. We know that 6,300 is too small. It's an underestimate, right? Where do you think the answer is? About halfway in between those? Well, let's check. Now, this is a midpoint. Notice on this one, it's telling you how many subintervals. What does this mean right here? It says 2 subintervals. What does that mean? It means 2 rectangles. Right? So I'm going to go to the middle. Right? There's the middle. And on each side, I'm going to use the dot that I know that's center. Do you see how we got those rectangles? We went, here's my side. I had to put that in because it says 2 rectangles, so I divide it in half. And then I pick the dot I know that's in the middle. It's not quite in the middle, but I have to go with the dot I know. I know that point because I was given a table. Okay, so what's the size of this rectangle? It's 50 times what? 100 plus 50 times 50, right? And if we add those up, what do we get? 5,025, 75? Okay. Now, before we go on to trapezoid, I want you to look back and I want to look for a pattern. Like I said, you're not going to want to draw these out for all your data. So tell me the difference in between my left and my right, my blue and my green. What do you notice is different about the numbers? Did the X's, did these all stay the same? Were those the same on both? And what is that number? If you look here, isn't that just the difference in your X's? True? Now, what do you notice about the heights? I'm going to put a little H above all those. Right? I want you to look at the heights and I want you to look at the table and tell me how you could easily find these without drawing rectangles. What do these heights correspond to on the table? The Y values, right? Notice the first one, the second one, we do all of them except the last one. Now, what do you notice about these heights? Let's mark them. 100. So what pattern can you come up with so you don't have to draw these? The right Riemann, or the left Riemann sum is going to start with the very first Y, and you're going to use every Y. The right Riemann sum is not going to use the first Y because it's using the right side. So you're just going to start one down and you go all the way to the end. You see how you could do that without having to draw this? It's just 20 times 120, 30 times 100, 30 times 80, 20 times 50. If I were doing a right Riemann sum, then I'm 20 times 100, 30 times 80, 30 times 50, 20 times 20. So you're just going to take that difference and multiply it. It's just you have to look at the numbers and know to start with the first one for left and start with the second one over for right. Does that make sense? Do you see that pattern? Okay. Now we have trapezoidal. We're going to look for a pattern with that too. So what are we going to do with this one? I need a new color. We'll do purple. So I'm going to use the numbers I'm given, right? And these are my X's. Notice my lines always correspond to these X values. So now instead of using left or right, I'm going to erase this in a second, so I'm writing pencil. This would be a left one. This would be a right one. They both are off a little bit, but a trapezoid I just draw. Now, how good does that look? That looks almost perfect, doesn't it? So what is the height of all of these? Remember, the height is this part. So what's the height of this track? Because the trapezoids are like this, right? This is the height. That's base 1, base 2, base 1, base 2. So the height here is what? 0 to 20 is 20. The height here is 30, 30, 20. What do these numbers correspond to? They correspond to the difference in x, correct? Now, area equals 1/2 base 1 base 2 times height. I write too big. Right? Now, base 1 is 120 plus base 2 for this one is 100. Now, for this one, this side is 100. This side is 80. Now, for this next one, this is 80. This is 50. And lastly, this is 50. We just looked. And that one is 20. What do you notice about those numbers? They match up exactly with, oops, they match up exactly with y, don't they? Do you see how to do that? It's 120 plus 100, 100 plus 80, 80 plus 50, 50 plus 20. Do you see from the picture why that is? Because you don't want to draw this picture every time. You want to be like, okay, my height is 20. My width is going to be, I'm going to add these two bases together and multiply by 1/2, right? So punch that into your calculator and tell me what you get. Go, go, go. We're adding those up. And was your prediction correct? Was the trapezoidal sum more accurate? It was, wasn't it? And you could have figured that out. 7550 is pretty much right in between 8800 and 6300. The midpoint got pretty close, but if you really want to be close, we want the trapezoidal. Do y'all see how all of these go together so you could just use a table and not have to draw a diagram? You could draw a diagram if you wanted, right? Anyone need a minute to write your thoughts down? Okay. Hopefully you can see that the more rectangles you create, the better the approximation will be. Ideally, we would like the number of rectangles to go to infinity, which really can't happen. Here's where limits come in handy. The appropriate, proper, fancy way to say this is the exact area under a curve. Notice when we draw rectangles or trapezoids, we're estimating. Calculus is exact. So the limit as n approaches infinity, what this means is if you could draw infinitely many rectangles, you would have exactly. We use calculus. This right here is what you've been practicing when you integrate. So when you have a formula and you integrate this, right? Let's say from 0 to 5. If I gave you a picture from 0 to 5, right? If you integrate this, you're finding the area right here. What else happens when you integrate? We need to write this down. It's been a while. Integration removes the rate. So if I say I'm running miles per hour and I integrate that equation, it gives me miles. It takes the per hour off. So if I said you were doing math problems and I had a formula for you and I integrated and I figured it out, if you were doing 20 per hour, I could put time in and it would tell me how many problems you got done because integration would take the per hour off. Okay, so let's look at a real problem. This is an old AP problem. A test plane flies in a straight line with positive velocity in miles per minute at time t minutes where velocity is a differentiable function of time. Selected values of velocity for 0 to 40 minutes are shown in the table below. So y'all tell me, if we're going to integrate, right? If this is miles per minute and we're going to integrate it, what is our answer going to be? Answer will be miles. Okay, we talked about that earlier, but you may have forgotten. So when I put this symbol on, this was miles per minute. This removes the rate, and now I'm left with just miles. So that's how I get my answer with integration. I want to know how much area is there? How many miles did you go? How many cupcakes did you bake? How many math problems? Whatever I want to know, right? If I have a rate, because what is a rate? A rate is a derivative. And when we integrate, we're taking the derivative part off, right? This is a derivative. We're integrating and going backwards back to the unit, just to put the whole thing in perspective. So use a midpoint Riemann sum with 4 subintervals of equal length. This means 4 rectangles, if you will. Right? 4 rectangles. So we got to make them even. Now, don't write this down. I'm going to not do it right the first time. If I did this, if I use that rectangle, this one, and did 4, did I finish it? No. Okay. So I need to be bigger. You need to figure out how wide they need to be. So I need 4 even rectangles. So I'm going to do 1, 2, 3, 4. And they always share one, right? The reason they share is because if you think back to what we're doing, we're sharing this wall. A big mistake people will make is they'll do this. Don't do this. I just want to show you. They'll do this. You see how they didn't share a wall? Then you would have big gaps in between. So make sure your wall gets shared. So can you tell me how wide this is from 0 to 10? 10. How wide is it from 10 to 20? 10. 20 to 30? 10. 30 to 40? 10. And it did say equal length. So we know that that's 10, right? Now this wants us to use the midpoint. So for this group right here, right? For this grouping, I have 3 y values. Which one is in the middle? The 7, the 9, or the 9? There's my middle one, right? So that's the one I'm going to use. So we're going to have 10 times 9.2, right? And of course, I'm going to use the middle one on all of these. If it told, now let's look at this. If it told me to use a right, I would have used the 9.5. And if it told me to use a left, I would have used the 7. Do y'all see that? This is the left number. This is the right number. So that's the middle. 10 times 7. This is an AP, probably a non-calculator part. So they gave us tens to multiply by. Right? Y'all, since these are all tens, can I pull the 10 out and add up these little numbers? So add those numbers up. What do you get? What is that? 29? 22.9. And what's 10 times 22.9? So there you go. You could just multiply these out and add them. I think it's a little easier to add the small numbers. Doesn't matter. I didn't know if y'all noticed if you're multiplying by the same number each time, you can factor it out. If that wasn't a 10, it would make our math a whole lot easier, right? If it was a scary number. Okay, so that's a midpoint. Again, if we had used a right, we would have used the 7, the 9, the 4.5, and the 2.4, right? And if we had used a right one, we would have used this one, this one, this one, and this one. So you don't have to draw a picture. Now, using correct units explain the meaning. That means they want you to write a sentence. So one way would be the total distance. I actually don't need capital letters, do I? Traveled for the first 40 seconds was, oh, minutes. These are minutes, not seconds. That would be a fast plane. Was 229 miles. And you could reword that. You could say the plane traveled a total of 229 miles for the first 40 minutes, or from 0 to 40. But when they say explain, you do need a complete sentence that gives you all the facts. Okay? That's it. What are we doing? We are approximating. In this particular problem, you don't have an equation, so you can't just go integrate it like we did before. So we do it using sums. We could do left, right, trapezoidal, or midpoint, right? Okay. Are you good?